All right, we're in Unit 8, Acid Bases. We're on now question number 41. Let's get to the question. All right, you have acetic acid, water forming acetate. The pKa is 3.18 at 25 degrees Celsius. The equilibrium for the acid ionization of acetic acid is represented by the equation above. If 10 milliliters of 0.2 molar acetic acid react with 5 milliliters of sodium hydroxide, which of the following could be used to calculate the correct pH during the resulting solution? Okay, okay, this one is pretty tricky. Look, you want to do this. The pH is equal to the pKa plus the log of the A minus over the HA. Now I know that my pKa is 3.18, but notice that I don't know what my A minus necessarily is. Right here, I'm gonna have the log of, I just want to do 0.20 over 0.10, but that's not, those are not the correct numbers, because now my molarity is going to be, my molarity is going to be changed by these numbers. So the correct answer here, I believe, is C. And if you look at it, it's because these bottom numbers here are the new volumes, right? The volume of adding 10 milliliters and 5 milliliters together, and you're adjusting for it. This is your A minus over, your A minus over your HA. Now this question was just a little bit too involved on the math, and I didn't like it. Now I'll tell you what, I knew that this was good. These ones I knew were wrong, and the thing that I was looking for was that denominator, the 15 milliliters. But notice that the first one is going to give you, notice that the first one, notice that D. I want you to see these numbers. See that, and that, and that, and that. Okay, that just, it looked out of place to me, because now you're just going to multiply those. You're going to get a negative number there, and I was just like, wait, it just could not be right. So I just said, okay, D is out of the question just by logic. But the reason why there's a correction for this one and not here, I didn't want to work it out with an ICE table or a BCA to find out. So the correct answer is C here. All right. The equilibrium for the reaction between a weak base, and water is represented by the equation below. The table shows the pH of 3 solutions of that at 25 degrees Celsius. So notice that the pH is increasing or becoming more basic the more of this weak base that we use. Which of the following equations can be used to correctly calculate the pH of the solution of that much with that much? So there is, let's look at what this is. This is NH. It ends with the NH. This ends with the NH2. So this is your weak base, right? But this is its conjugate acid. All right. So how do you find the pH? You have to have the H plus concentration. So to be able to know the H plus concentration here, we're gonna have to take to find out the H plus concentration here, we're going to go ahead and use the numbers that they gave us. We know that HA is equal to A minus, yes? 0.1. So using the Henderson-Hasselbalch, pH is equal to pKa. Okay? Now, if the pH is equal to the Ka, well, here's another thing. The Kw is equal to the Kb, times the Ka. Given this information above here with that Kb, so 1.0 times 10 to the negative 14 divided by that Kb, which is 5.4 times 10 to the -4, that will give you your Ka value. Now, we don't actually need to figure out that number, but I know that if right here, I'm saying that the pH is equal to the pKa because this and this were equal, okay? My pH is equal to my pKa. Well, so if I want to find my pH, I got to find the negative log of my Ka, and then my Ka is over here. This is I got to find the negative log of this thing. The correct answer is A. There was a lot going on this question. You needed to know that your A minus and your HA were equal to one another, and that you needed to know that Kw is equal to Ka times Kb. All right, 43. 43, based on the information given, which of the following is true? Solutions with higher concentration of this base and a higher pOH. Solution with a higher concentration of a base have a higher pOH? No, it would have a higher pH, so I know that this is not true. Solutions with a higher concentration of this base have a higher pOH. Again, not true. It would have a higher pH, so it's between C and D. Let's read C. Solutions with a higher concentration of that weak base have a higher pH. That's true, because to reach equilibrium, the small amount of the conjugate acid is produced. To reach, if we have to produce more conjugate acid, we're not going to have a higher pH. Okay, so that's not true. The answer is D. Solutions with a higher concentration of a weak base have a higher pH because to reach equilibrium, more OH minus is produced. That makes more sense. That's what's making it basic. Okay, number 44. Wow, this is a lot of reading. Okay, student mixes 100 milliliters of 0.2 of a weak base and 0.2 of its conjugate acid, and claims that if a small amount of the strong base is added to the mixture, then the resulting change in the pH mixture will be smaller than the resulting change in the pH would result from adding the same amount of strong base to, okay, so up here we have a buffer, right? I should use a highlighter. Up here we have a buffer. This is your buffer, okay? Down here, this is your weak acid. Which of the following best explains whether or not the student's claim is correct? So the student says, the student here is correct because, look, if you add a strong base to both of these things, the buffer is going to accept it without changing very much. So the correct answer was B. The claim is correct because the mixture contains a significant amount of the acid, which can react with and partially neutralize the added strong base, thereby reducing the change in pH in 0.2 molar weak acid. The concentration of the acid is very small, therefore the added strong base is not neutralized and the change of the pH will be larger. The answer is B. That's how a buffer works, and that's just kind of a really verbose way of saying how a buffer works. All right, number 45. You have, again, another weak acid. The chemical equation above represents the acid ionization equilibrium for this weak acid, for which pKa is 4.8. Which of the following is the best estimate of the pH of the buffer prepared by that much and that much, that much and that much? Okay, whoa, this is a good question. I love this. pH is equal to pKa plus the log of A minus over HA. Now, your A minus is this. Your HA is this. Which one do I have more of? I have 100 milliliters of both, but notice that my concentration of my A minus is less than the concentration of my HA. So that means the log is going to be, again, A minus is going to be very little, but the HA is going to be a whole lot, okay? And I really want you, okay, I know, why am I not putting this into a calculator? Because this is a non-calculated portion of the test. Now, this thing right here, when you have less numerator than denominator, you got to know that when you take the log of that, that's going to be a negative number. I don't know what the number is, but it's going to be negative. And my pKa is 4.8. So if I have pH is equal to 4.8 plus a negative number, it's going to be lower than 4.8. The answer is going to be B. Now, some of you guys go, well, it's lower. Well, and if you didn't use a calculator, how do you know it's not A? How can it not be 1? That'd be a real big problem if your acid, which is a weak acid, right? You have a weak acid, and you're going to tell me you have a pH of 1, then you just don't understand the concept. Like to have a pH of 1 and be a weak acid, well, you have to be a strong acid. Not going to happen. The answer is B. Okay, 46. Which of the following is a correct mathematical expression used to calculate the pH of 1 point molar BA? Okay, so I like saying Mickey Mouse ears for this, okay? Say you worked at Disneyland, or you manufactured Mickey Mouse ears for everybody. If you have 100 of these, how many headbands do you have? You have 100. If you have 100 of the Mickey Mouse ears, how many ears do you have? You have 200, okay? So if you have 0.10 molar of BaOH, 2, you have 0.10 molar of Ba2 plus. And then you have 0.2 molar of OH minus. So notice that that number has to double there because this OH minus has a 2 coefficient, okay? So let me shrink this down a little bit, get it out of the way. All right, so if we have, okay, the correct answer is, how do we find the pH? Well, we have to find the pOH first. So we got to take the negative log of the OH minus, right? That will give us the pOH. And then to find the pH, we'll have to subtract that from 14 is equal to 14 minus the pOH. The correct answer here is D. But isn't that symbol wrong? I think they meant to put negative. I think they messed up there. But they're saying the answer because that would be the pOH, pH plus pOH. So they screwed up here. This symbol should be a negative, unless I'm going crazy. But okay. All right, number 47. A student prepares a lactic acid sodium lactate buffer solution by mixing 40 milliliters of 0.5 acetic acid with 200 milliliters of 1.0 Na sodium acetate, or I don't even know what that is, sodium lactate. The pKa of that is 3.0. What is the resulting acid? Okay, so look, which one do I have more of? I have more of this than of that, okay? Because I have 200 milliliters of one instead of 40 milliliters of 0.5, right? So I have, okay, so again, Henderson-Hasselbalch pH is equal to pKa plus the log of my A minus over my HA. So in other words, we said we had more of this, which is the A minus, okay? If you take the log of something that has a bigger numerator than it does a denominator, right, this is going to be some kind of positive number. And the pKa is 0.0308, right? So pKa plus a positive number is good. The pH is going to be greater than 3.08. The answer turns out to be C. Ooh, no, it doesn't. No, it doesn't. Hold on. Let me check. Oh, shoot, it doesn't. All right, let's do it. Now I actually have to do the numbers. Okay, 40 times 0.5. Okay, that becomes 20. 200 times 1 is 200. So this is that. You're going to have the log of 10. And if you guys don't know what the log of 10 is, well, it's 1. Okay. So this is going to be 3.08 plus 1. They wanted you to know how to do that, which is means this is not the correct answer. That is the correct answer. So it's going to be the answer is going to be 3.08 plus 1. And that's tricky. That's tricky. You actually had to do the math and the numbers for that one. So, all right, let's go to 48. Which of the following statements about pH of 0.10 molars of a strong acid is correct? Okay. Your pH, okay, so your concentration of your H plus is equal to 10 to the negative pH. Oh, shoot, what am I doing? Wrong way, sorry. Your pH is, okay, if you have 0.01 HClO4, that means you have 0.01 H plus, and you have 0.01 ClO4. Okay, this right here is huge because it's the same number because this is a strong acid. It disassociates completely. And people are, you guys are saying, wait, how come this is, you say brickle-no-so-clo. When I say clo, I mean ClO3 and ClO4, chlorate and perchlorate are both considered strong. But anyways, here's your H+. So you have to take the negative log of 0.01. Now, okay, I've been trying to avoid actually doing a log with you guys, but all right, let's do it. So this is negative log, and if you guys remember, this is called it's called the log roll. You guys remember that? You say A to the C is equal to B, okay? Now, this is a log base 10 here, so we're saying, and then we're trying to find out what it means, so let's do the log roll of 10 to the x is equal to 0.1. So 10 to the x is equal to 0.01. That's how you do a log. And 10 to the 0 is 1, 10 to the negative 1 is 0.1, 10 to the negative 2 is equal to 0.01. So x, in other words, is negative 2. Okay, so the answer. So your H plus. Yeah. So if you're doing that, if you're doing the negative log, it'd be negative 2. So the correct answer here is A. pH is equal to 2 because H plus is equal to 1.0 times 10 to the negative. Okay, let's go to question number 49. Okay, 49. HF plus water yields H3O plus F minus. Ka is equal to 6.3 times 10 to the negative 4 at 25 degrees Celsius. The acid ionization equilibrium for HF is represented by the chemical equation above. A student claims that the pH of a solution that contains 0.1 molar HF and 0.1 molar NaF will change only slightly when solid amounts of acid bases are added. Which of the following equations can justify the use of this claim? We've done a couple of these problems, but this is basically saying this is the buffer. You have to have your acid, HF, and you have to have its conjugate base. Okay, so let's take a look at the answers, or possible answers. The answer is going to be D. Here's your acid acting like an acid, but here's your conjugate base bringing back to your acid. Okay, so those are the two equations that, look, the F minus in this scenario, here, let me show you. The F minus here is going to consume the H plus, which is going to allow it to go backwards to create more HF, which will always balance your equilibrium. Okay, number 50. Which of the following pairs of mathematical expressions can be used correctly to calculate pH and pOH of a, okay. If I want to find the pOH, I will have to take the negative log of my OH minus. And my OH minus, this is, remember, K is a spectator, it goes away, right? So this is really, my concentration of my OH minus is 0.0015, right? So I have to take the negative log of that to get my pOH. Okay, let me see. Negative log, okay. So pOH is not equal to that. Looks like A, B, and C are still in play. Now, to get my pH, I have to get 14 minus, all of this guy. But it's, oh, shoot, it's minus the negative log. Shoot, that's the answer to that past question, why I did it wrong. I was not wrong. I was wrong, not the question. That's why. So, okay, I don't know if I don't remember what question it is. So I said that they might have made a mistake. They didn't. This becomes the negative log 0.0015. So this negative becomes a positive there. Oh, that's tricky. Anyways, so the correct answer is C. Yeah, that negative log, that's really cool. I forgot what question I was talking about, but that was the one that I thought was they made a mistake, but they didn't. I made a mistake. Okay, we're on that was question number 50. Oh, wow. Okay, this is a big thing to read. A 0. Or we're on 51. A 0.35 gram sample of Li is placed in an aeromite flask containing 100 milliliters of water at 25 degrees Celsius. A balloon is placed over the mouth of the flask to collect hydrogen gas that is generated. After all the Li has reacted with H2O, the solution in the flask is added to a clean, dry burette and used to titrate an aqueous solution of monoprotic acid. The pH curve for this titration is shown in the diagram below. Okay, weak acid, strong base. On the basis of the curve, the pK value of the acid is closest to. How do we find the, okay, so here's the equivalence point. The equivalence point is at 25. Then that means the halfway equivalence point is at 12.5. And that number, it's almost 5. Yeah, it's almost 5. Answer is B. And that is, you know, you're literally eyeballing it. Look, don't, it's not a math test, okay? So don't get caught up in like, what's the formula that I use? You just got to know that the pH is equal to the pKa at the halfway point. And where's the halfway point? Well, it's halfway, or the halfway equivalence point, which would be half of 25 because the equivalence point is clearly right there. All right, 52. Again, you have nitrous acid. Nitrous acid reacts with ammonia according to the Balanced equation, chemical equation shown above. If 50 milliliters of 0.2 nitrous acid reacts with 50 milliliters of 0.2 NH3, okay, weak acid, weak base are mixed and allowed to reach equilibrium. What is the approximate NH3 at this? Okay, this was really hard for me. I actually don't know how to solve this one. Because a weak acid, weak base, I'm pretty sure you have to do an ice table for this, but I kept getting the wrong answer, so I'm going to tell you guys to be continued. They say that the correct answer is A. If anybody figures this out, please show me how to do it, and I will be at your mercy. Number 53. H2 gas and N2 gas are placed in a rigid vessel and allowed to reach equilibrium in the presence of a catalyst according to the following equation. You have that. The diagram below shows the concentrations of H2, N2, and N3 and the changed over time. More NH3 gas is added to this at time 2. The temperature is held constant. Which of the following most likely will occur? Okay, so if you add more NH3, so NH3 is that middle line, it's going to spike up initially, and then it's going to start going back to equilibrium, right? Then that's going to make the N2 slowly increase. It's going to make the H2 slowly increase, right? Because they're a ratio. Okay? So the answer, the value of the equilibrium constant, the K is not going to change. K can only change with heat, and so the equilibrium constant will neither increase nor decrease. The total pressure in the container will not decrease. The pressure is going to increase because you just added more gas. Okay? The amount of N2 will increase. That is true. The H2 will decrease. That is not true. Okay, the N2 is going to start. It's going to start increasing because you just put more more of this substance in. Now it's going to equilibrate and get back to equilibrium. All right, 54. Which of the following was true for the system between time 1 and time 2? The concentration of N2 decreased. Nope, because it was at equilibrium. The temperature of the system decreased. Nope. The number of effective collisions between N2 and H2 and N2 was 0. It's not 0. It's still happening. The rates of the forward and reverse actions were equal. Yes, that is true. That is the definition of equilibrium, that the forward reaction and the reverse reaction are equal. Okay, mixtures that would be considered buffers would include which of the following? Buffers are when you have a weak acid and its conjugate base. So let's look at this. This is a strong acid and its conjugate base, but it's strong. This is a weak acid, and here is its conjugate base because that Na goes away. Okay, here is another strong acid, and it's salt. So no, so the only correct answer is number 2, or Roman numeral 2. The correct answer there, or let's look at your answer choices, is B. All right, let's take a look at number 56. How can 100 milliliters, wait, no, I'm reading the wrong question. Okay, there you go. The equation above represents the acid ionization equilibrium for HF. To prepare a buffer with pH of 3.5, 4.2 NAF should be added to that much HF, the buffer is accidentally prepared using 90% pure NaF instead of 99% pure NaF. Assume that the impurities in NaF are sample and inert. Which of the following explains how the error affects the pH and the capacity of the buffer? Okay, so look, here is your acid, and here is your conjugate base. So Henderson-Hasselbalch wise, we're talking about pH is equal to pKa plus the A minus over your HA. So I don't know what your A minus is, but we accidentally used a 90% pure NaF, not a 99% pure NaF. So this A minus here is lower. Yeah. So okay, so your pH is like 3.5, which let's say your pKa, I don't know, was like it's just some number, okay, close to 3.5. But if your A minus goes lower, and you have to take the log, sorry, I didn't write log. You have to take the log of this. Then if your A minus is lower, if your numerator is lower, this becomes closer to a negative number. So the correct answer is C. The pH is slightly lower than 3.5 and has lower capacity for the addition of acid because less than 4.20 NaF was added. We didn't actually add 4.2, we added 90% of 4.2. Okay, so that would lower our pH because we didn't put as much conjugate base, allowing more H plus to come around. If more H plus can come around, then you're going to become more acidic. 57. All right, let's look at this. Your initial NH3, and you doubled it. When you doubled it, your equilibrium went there, so this would also be 2.3 times 10 to the negative 3. You're going to have more OH minus. You're going to have, okay, first of all, if you have more OH minus, then you have a lower POH, right? So your POH should be lower than your POH should be lower than 2.78 because if you have more if you have more OH minus, then your POH, you are becoming more basic. Okay, meaning you have a a lower POH. The correct answer is C. Your OH minus, okay, obviously your OH minus has to be equal to your NH4 plus. These things have to be equal, so it has to be C or D. And it's just saying the correct thing there. Oh my goodness. Okay, number 58. How can 100 milliliters of sodium hydroxide solution with a pH of 13 be converted to sodium hydroxide solution with a pH of 12? Okay, so what are we doing here? We're changing our pH by 1, right? By 1. And remember, this is a logarithmic function of base 10. So if you're going from pH, okay, so a pH, this H plus is equal to 10 to the negative 13. But, okay, this H plus is equal to 10 to the negative 13. But this H plus is equal to 10 to the negative 12. And what are we talking about? We're talking about concentration. So concentration is moles over liters. So you know how you can get this number? Yeah. Do you know how you can get this number to become lower? Is that you increase the liters of water, right? So the correct answer is, let me see, is it C? By diluting the solution with distilled water to a volume of 1 liter. You would have changed the volume from 100 milliliters to 1,000 milliliters, right? You would have, by a factor of 10. So how would you get 13 to become 12? You would divide it by a larger number. 59. Concept question, okay. The acid ionization equilibrium For the weak acid, HF is represented by the equation above. To prepare a buffer with a pH of 3.5, a student needs to mix 250 milliliters of 0.1 molar HF and 250 milliliters of 0.1. So he has a buffer solution. If the student accidentally does 250 milliliters of 0.05 and 200 milliliters of 0.05, okay, well, it's not gonna change the pKa or the pH, but it's just not gonna be gonna buffer as much. So the answer is not C or D. It has to be between A and B. So let's read A. The buffer will have a lower capacity. Yeah, it can't do as much because the smaller amount of moles of H and F minus able to react if an acid or base is added. That is correct. A, not B. All right, last one. A student mixes 40 milliliters of 0.1 molar HBr with 60 milliliters of 0.1 KOH. Okay, that means that, okay, look, this basically neutralized, but you're gonna have 20 milliliters of 0.1 OH minus left over, right? And honestly, if this is molarity and moles, then to find, oh, this is interesting. 0.02 times 0.1 gets you 0.002, right? Because changed it to liters. That's how many moles you have. But when you mixed these solutions, 60 milliliters and 40 milliliters, you get a total of 100 milliliters or 0.1 liters. This turns out to be C.